Here's where we've gotten to in the completeness theorem proof so far. Recall that we're proving this claim that if gamma is consistent in SD, then gamma is truth functionally consistent. Or in other words, if it's not possible to derive a contradiction from gamma in SD, then there must be a truth value assignment that makes every sentence in gamma true. Remember that this isn't exactly what the completeness theorem says, but this claim does have the completeness theorem as an immediate consequence. So it's totally fine that we're proving this instead of the completeness theorem as it's usually stated. Okay, so last time we built this infinitely large set called gamma infinity, and we showed that gamma infinity is maximal consistent in SD. I always get a little bit confused about the grammar here. I'm not sure if it's supposed to be maximal consistent or maximally consistent. I see it written both ways a lot. I think I see it written maximal consistent more, so that's what I'm going to stick with. But yeah, it does sound weird when I say it out loud. Okay, so we show that gamma infinity is maximal consistent in SD. And remember that maximal consistency has two components. First, a maximal consistent set is consistent in SD. And a maximal consistent set is such that if you take any sentence that isn't already in the set and you add it to the set, then the set would end up being inconsistent. Okay, so there's nothing else we can add to the set that is so infinitely large to make that would still keep the set consistent. Okay, anything else would make it inconsistent. All right, so now we're answering the next question, which is what was the point of building a maximal consistent in SD set? Well, remember that our aim is to get from this claim about consistency in SD to this claim about truth value assignments. So we know that gamma infinity is a set that's consistent in SD, right? So we have the antecedent. And the reason why we made gamma infinity into this set that's so big is because it's going to turn out that being a member of gamma infinity is just like being true on a truth assignment. And that's the idea we're going to flesh out today. But notice, so when we say that something is truth functionally consistent, what we're saying is that there's a truth value assignment that makes every member of the set true. So if we can show that being a member of gamma infinity is just like being true on a truth assignment, then we will have proven that the consequent holds when the antecedent does. Okay, so that was the point of building gamma infinity. So our goal today is to prove that being a member of gamma infinity is just like being true on a truth assignment. And now let me explain in a little bit more detail what that means. So here I've written out exactly the things that we know from learning about the truth tables of each of the 5 logical connectives. Okay, so say that S1 and S2 are sentences of SL, and W is a truth assignment. So let's start with this first claim. Not S1 is true on some truth assignment W, if and only if S1 is false on W. We know that from the truth table for the negation. So here it is, just for us to get our memories jogged a little bit. So S1 is either true or false. And when S1 is true, not S1 is false. And when S1 is false, not S1 is true. Okay, so if not S1 is true on a truth assignment, so that's here, then it must be the case that S1 is false. Okay, and that's exactly what this first line is telling us, right? So it's just pointing to the line on the truth table where not S1 is true and saying, what does that say about S1? Okay, so once again, all of these claims in what I've written down here are just things that we know from the truth tables of each of logical connectives. Let's do one more just to be sure. So this next line says that S1 and S2 is true in a truth assignment if and only if S1 is true on the truth assignment and S2 is true on the truth assignment. And we know that again just through the truth table for the ampersand. So here it is, right? And remember that the ampersand only gets marked true on one line of the truth table, and that's the case where both of the sentence letters, both of the conjuncts are true. Okay, and that's exactly what this line here is saying. It's saying that in order for S1 and S2 to be true on a truth assignment, it must be that both of the components are true. Okay, so I won't go through the rest of them, but the pattern is exactly the same, right? These are just describing the conditions under which each compound sentence is true on a truth assignment. Okay, so here's what I mean when I say that being a member of gamma infinity is just like being true on a truth assignment. This is called the regularity lemma, and it's called the regularity lemma because you'll notice that it follows the exact same pattern as the one that is above. So in this first line, we have the claim, not S1 is a member of gamma infinity if and only if S1 is not a member of gamma infinity. Okay, so if you look up, right, to this first line that we analyzed, you'll notice that the only difference between them is that the phrase is true on W gets replaced with is a member of gamma infinity. And wherever you see is false on W, we replace that with is not a member of gamma infinity. Otherwise, the pattern is exactly the same for each of them. So that's why being a member of gamma infinity is just like being true on a truth assignment. Unfortunately, we don't get to help ourselves to the regularity lemma. We have to prove it case by case. So we have to do 5 cases, one for each of the logical connectives, right? So negation, ampersand, wedge, horseshoe, and if and only if. And that's what we're going to be doing today. What I'm going to do is I'm just going to go over 2 cases of the regularity lemma proof. I'm going to go over ampersand and if then. The problem set asks you to do 2 more cases. It asks you to do the disjunction case, and it asks you to do a case involving like a fictional, something that's not actually a rule of SD, but that works as a rule of SD, so you can provide a proof for it. But I'm just going to do these 2 cases here to illustrate how to go about doing this proof. Okay. In order to do the proof for the regularity lemma, we're going to need a useful fact. And the useful fact is called JOVE. And the reason why we're calling it JOVE is because several times in the proof you'll have to say, by Jove, which is something that people used to say. I looked it up on Urban Dictionary. Apparently it was like rude to say God in conversation. So instead of saying by God, people would say by Jove. So it's kind of like a exclamation. Okay, well anyways, so we're going to appeal to this useful fact called JOVE. And here's what JOVE says. If gamma allows you to derive P, and gamma is a subset of gamma infinity, then P is a member of gamma infinity. There's a special case of JOVE in particular that's of interest to us, and that's this case. If gamma infinity allows you to derive P, then it's going to be trivially true that gamma infinity is a subset of itself, right? So we can just ignore that part. Then P is a member of gamma infinity. All right, so what does this claim mean? Well, let's give a brief sort of little proof of it. So we have this set gamma infinity we know is maximal consistent, and we know that gamma infinity allows us to derive P. So then we ask the question, is P a member of gamma infinity, right? So this is what we're asking. And the answer has to be yes, right? It must be the case that P is a member of gamma infinity. And naturally, the next question is why? Why does P have to be a member of gamma infinity? Well, let's say that P is not a member of gamma infinity. Because gamma infinity is maximal consistent, that it must be the case that gamma infinity union P allows you to derive contradictions, right? Because if P isn't in gamma infinity, then adding it to gamma infinity would allow you to derive all sorts of contradictions. So let's say that allows you to derive R, and it also allows you to derive not R. Okay, well, once you have this fact, once you have a contradiction, you can get whatever you want, right? And in particular, in this case, what we want to get is not P. So we can set up a derivation that looks like this. So here we have all the assumptions in gamma infinity as our premises, right? And we then assume in a subderivation P. Okay, and that's what gamma infinity union P means. It means we take all the assumptions gamma infinity and add this extra assumption P. So we know that P, because gamma is maximal consistent and P is not a member of gamma infinity, that adding P to gamma infinity would allow you to derive contradictions. So we can get R and not R. But then we can use negation introduction to get not P, right? So what this proves is that gamma infinity union P allows you to also get not P. So therefore, if you assume that P is not a member of gamma infinity, then gamma infinity is not maximal consistent, right? Because it has a contradiction in it. So it must be the case. So P must be a member of gamma infinity. So we did a reductio argument where we assumed the opposite of what we wanted. We got a contradiction, and that allowed us to get what we wanted to show. So this is a shortened version of the proof of JOVE, but all that you need to know is this, right? If gamma infinity allows you to derive a sentence P, then P must also be a member of gamma infinity. And we're going to be appealing to JOVE a lot in our proof of the regularity lemma. Here is how you prove each case of the regularity lemma. This might sound kind of like gibberish right now, but it's going to become a lot clearer once we do a couple of cases of the proof. Okay, so here's how you prove each case. If you are told that a sentence is in gamma infinity, then what you do is you use that sentence that you're told is a member of gamma infinity to derive what you want from gamma infinity, and then use JOVE to show that the sentence you want must be in gamma infinity. So remember that JOVE takes you from a claim about being derivable from gamma infinity to a claim about being a member of gamma infinity. So that's why we use JOVE at the end, right? Because ultimately we want to prove claims about membership in gamma infinity. Okay, now in the second scenario, if you are told that a sentence is not in gamma infinity, then you use that fact to, you use the fact that adding the sentence to gamma infinity would allow you to derive a contradiction to get the sentence you want, right? So remember that whenever you get a contradiction, you just assume the negation of the thing that you want, reiterate the contradiction, and discharge the thing that you want. Okay, so we're going to use that fact in order to get what we want when we're told that a sentence is not in gamma infinity. And then, just like as before, we're going to use JOVE to get from that claim about being derivable from gamma infinity to a claim about being a member of gamma infinity. Okay, again, that might sound like gibberish, but we're going to go through two cases that will hopefully make this pretty concrete. We're going to start out by proving the case with the ampersand. So I'm going to scroll back up and remind everyone that this is the claim that we're proving. Okay, so we have to prove each case of the regularity lemma, and there are 5 cases. So we're proving this biconditional claim first. So I'll write it back down here. So we're proving the claim. So this is the and clause of the regularity lemma. And the claim is that if, P and Q is a member of gamma infinity. I switched from S1 and S2 to P and Q just because it's like easier for me to keep track of P and Q in my head. Okay, but it doesn't matter what meta variables you use. So P and Q is a member of gamma infinity if and only if P is a member of gamma infinity and Q is a member of gamma infinity. Okay, so that's the claim we're proving. This is a biconditional claim, right? It's an if and only if, so we have to prove both directions. So we'll start out by going in this direction. So the first thing you do is you assume the antecedent of what you're proving, right? So in this case, since we're going to the right, we're going to assume the left side. So say that P and Q is a member of gamma infinity. And now we want to prove the consequent. Right, so our aim is to show that starting from this assumption, we can get to P as a member of gamma infinity and Q as a member of gamma infinity. And the way we do that is by following the instructions up here. So in this case, we are told that a sentence is in gamma infinity. So we're in this scenario up here, right? Because we're told that P and Q is a member of gamma infinity. Okay, so the next step is to use the sentence to derive what we want from gamma infinity. Well, that's actually going to be pretty easy, right? So we want to derive P and we want to derive Q. And because we know that P and Q is a member of gamma infinity, then it's going to be a simple application of conjunction elimination. So here's one scenario. A set containing P and Q allows us to derive P, and a set containing P and Q allows us to derive Q. And I'm going to draw one derivation for each of these just to reiterate why that's the case. So let's say P and Q are your assumptions, then you can easily derive P from an application of conjunction elimination. And similarly, if P and Q is your assumption, then you can easily derive Q through conjunction elimination. Okay, so what we can say is, so we know that P and Q is, the set containing P and Q is a subset of gamma infinity, right? So we know that gamma infinity allows us to derive P, right? Because we assumed up here that P and Q is a member of gamma infinity. And what this derivation tells us is that gamma infinity allows you to derive Q. Okay, now we're in a position to apply JOVE, right? So JOVE says that if gamma infinity allows you to derive something, then that thing must also be a member of gamma infinity. So we write, so by Jove, using the exclamation. P is a member of gamma infinity, and Q is a member of gamma, Q is a member of gamma infinity. Okay, and that proves exactly what we wanted, right? We started from the antecedent up here, and we ended up with the consequent down here. All right, so that completes one direction of the proof. Now we have to do the other direction. So we point the arrow in the other direction, and now we assume, so say that P is a member of gamma infinity, and Q is a member of gamma infinity. So that's our antecedent now, and we want to get to the claim that P and Q is a member of gamma infinity. So again, we're starting with a claim where we're told that a sentence is in gamma infinity. So we're going to use the same pattern. We want to show that we can construct a derivation where if we know that P and Q are both members of gamma infinity, so we have a set containing P and Q, from that we can derive P and Q. And that's pretty easy to do, right? So here it is. We have P and Q as our assumptions in gamma infinity, and then we can derive P and Q through a simple application of conjunction introduction. Because P and Q is a subset of gamma infinity allows us to derive P and Q. Okay, and now we're in a great position to apply JOVE. So we're going to go from a claim about what gamma infinity allows us to derive to a claim about membership in gamma infinity. So by JOVE, P and Q is a member of gamma infinity. Okay, and that completes the case for the conjunction, right? We did both sides of the biconditional. That's it. Cool, pretty simple. Okay, so now we're going to do one more case. We're going to do the conditional case. So you can scroll up to the part with the regularity lemma, but I'll just write down what the claim is here. So it's the horseshoe case, and the claim is if P then Q is a member of gamma infinity, if and only if P is not a member of gamma infinity, or Q is a member of gamma infinity. All right, so again, this is biconditional. Let's do the direction going to the right first. That means we're taking this and assuming it, and then we're trying to get there. All right, so let's assume that if P then Q is a member of gamma infinity. All right, and then we want to prove that it's either going to be the case that P is not a member of gamma infinity or that Q is a member of gamma infinity. Okay, so the first thing to note is that either P is a member of gamma infinity or it's not a member of gamma infinity, right? That's just like, those are the only two options within the space of logical possibility here. If P is not a member of gamma infinity, then we're done, right? Because then the disjunction is fulfilled. So we'll write that down. If P is not a member of gamma infinity, then we're done. Okay, so one side of the disjunction is fulfilled. So let's say that P is a member of gamma infinity. Okay, and now we want to prove that we're going to be able to get this side, that we're going to be able to show that Q is a member of gamma infinity too. All right, well, how do we do that? We're in a scenario, just like we were before, where we're told that a sentence is a member of gamma infinity. So that means to scroll all the way up here, we're in this scenario again. So we're going to use the sentences we're told that are in gamma infinity in order to, whoa, sorry, that was crazy. In order to construct a derivation that gets us what we want. So here's how we do that. We want to get Q, right? And we know that if P then Q is in gamma infinity, that's what we assumed up here. And we also know that P is a member of gamma infinity. That's what we assumed down here. So we have a set that contains if P then Q and P. And from that, it's going to be pretty easy to derive Q. Here's how, right? So if our assumptions are if P then Q, and then we also have an assumption P, then we can derive Q through a simple application of conditional elimination. Okay, so what that shows is that gamma infinity allows us to derive Q. And that's because we know up here that if P then Q and P are members of gamma infinity. Now we're in a position to apply JOVE, right? So we can go from this claim about what's derivable from gamma infinity to a claim about membership in gamma infinity. So, by Jove, Q is a member of gamma infinity. And now we've showed that one of the disjuncts have to be true, right? So either it's the case that P is not, either P is not a member of gamma infinity, right? Or if P is a member of gamma infinity, if P is a member of gamma infinity, then Q is a member of gamma infinity. Okay. So then that proves the first direction of the claim. We showed that if P then Q is a member of, if P then Q is a member of gamma infinity, then either P is a member of gamma infinity or Q is a member of gamma infinity. Okay, time to go in the other direction now. So now we're going to assume that either P is not a member of gamma infinity or Q is a member of gamma infinity. And we want to show that no matter which of these is the case, we're always going to be able to get if P then Q. Okay, so there are two cases here, and we're going to go through each one at a time. So call this case case 1. So case 1 is, say that P is not a member of gamma infinity. Okay, now we are in the second kind of scenario that I set up here. If you are told that a sentence is not in gamma infinity, then we want to use the fact that adding the sentence to gamma infinity would allow us to derive a contradiction in order to derive the sentence we want. Okay, so that's what we're going to do now. So we're told that P is not a member of gamma infinity. Okay, so then it's going to be the case. So then for some sentence R, gamma infinity union P will allow you to derive R, and gamma infinity union P will allow you to derive not R. Okay, so we're exploiting the fact that because P is not a member of gamma infinity, that if you tack on P to gamma infinity, you can derive a contradiction. Now that we can derive a contradiction, we can construct a derivation to show that gamma infinity allows us to derive if P then Q. So we can construct a derivation that shows that gamma infinity allows you to derive if P then Q. And here's what that derivation looks like. Okay, so up here you have all the assumptions in gamma infinity. And we did up here, we stipulated that we're going to tack p on. And what that means is we get to make a little subderivation with p as our assumption. Okay, so that's what this here means. And we know that gamma union p allows you to derive r and not r. So ultimately, we want to derive if p then q, and we know working backwards that means we have to use conditional introduction and get from p to q. How are we going to get q? Well, you can assume the negation of what you want and then reiterate the contradiction. So we assume not q for the purposes of negation elimination, and then we do negation elimination after we reiterate the contradiction, and that allows us to discharge if p then q through conditional introduction. Okay, so that proves that gamma infinity allows you to derive if p then q. So by JOVE, right, we can say that if p then q, I'm actually going to write, so by JOVE, if p then q is a member of gamma infinity. And we can conclude that because we showed here that gamma infinity allows us to derive if p then q. Now it's time to do case number 2 of this direction. So case number 2 says, say that q is a member of gamma infinity. So now we're back to the case where we're told that something is a member of gamma infinity. So all we want to show is that if you have a set containing q, that allows you to derive if p then q. And that's going to be a pretty simple derivation, right? So you assume q, and then you get to assume p for the purposes of conditional introduction, and then reiterate q, and that allows you to discharge if p then q through conditional introduction. So because q is a member of gamma infinity, the set containing q is a subset of gamma infinity. So that means that gamma infinity must allow you to derive if p then q. So by JOVE, if p then q is a member of gamma infinity. Okay, so that completes the first step of, oh wait, no, that's it. We're done. This was the second part of the biconditional. Okay, so that completes the proof for the material conditional case of the regularity lemma. So I would recommend writing down these instructions for what to do depending on what information you're given. I think that'll be really helpful. On the problem set, there are 2 questions about this that ask you to first, one of them asks you to do the disjunction case of the regularity lemma, and one of them gives sort of a fictional rule of SD and asks you to prove the case involving that rule. All right, that's it.